I'm Grady, and this is my column on computing, the incredible lightness of software. NASA's Voyager is an exquisite object of exploration and of engineering. From an explorer's point of view, Voyager 1 is the first human artifact to have waded into the shores of interstellar space. Launched in 1977 and expected to keep operating through 2020, Voyager has witnessed active volcanoes on the moons of Jupiter, mapped heretofore unknown regions of the heliosphere, and has presented us with our most distant selfie, the image of the pale blue dot, taken in 1990 from a distance of almost 40.5 AU, or slightly more than 6 billion kilometers from Earth. From an engineer's perspective, Voyager is a beautiful case study in the development of complex software-intensive systems. Voyager's computers were an evolution of a proven system, the Viking command computer subsystem. Because of the increased computational demands for its scientific mission, Voyager placed two instances of this computer on board, one for basic spacecraft hygiene and the other for attitude control, plus a third custom computer for flight data. As is typical for high-reliability real-time systems, each of these three systems was architected with two processors, and each built out of around 150 standard TTL integrated circuits. There existed a total of less than 70 kilobytes of memory for all three subsystems, and, in a first for space systems, the custom system used dynamic CMOS memory. Another important architectural decision, also novel for space systems, was the use of what at the time was called soft logic. Today, we call it firmware. Voyager's flight software was largely the product of just two members, Richard Rice and Edgar Blizzard. A software engineer, one thing that Rice said about his experience stuck out to me. "We didn't worry about top-down or structured," he said. "We just defined functions." Indeed, testable, measurable, executable software that works is always the most important artifact of any software-intensive projects. Developing software-intensive systems is always an incremental and iterative process, both within the lifespan of a single system and across entire families of systems. Voyager built upon the experience of the Viking project, a planetary mission to Mars, as well as that of Pioneer, whose missions were to explore Jupiter, Saturn, and beyond. In retrospect, it's clear that the impetus of both manned and unmanned space exploration led to pioneering discoveries not just in astrophysics, but also in the best practices of systems engineering. A number of serendipitous, unexpected connections punctuate the story of computing and space exploration. While at JPL, Jim Blinn developed animations of the Voyager mission flyby, critical for reasoning about the spacecraft's trajectory. His work also served to visualize the project, helping to inspire an entire generation via Carl Sagan's original Cosmos series. Among other things, Jim developed some of the fundamental algorithms in computer graphics, such as bump mapping and Blinn-Flong shading, and so doing, he helped lay the foundation for modern computer graphics. As for one of those curious connections, let's look at Flong shading algorithm and the Pioneer anomaly. After the Pioneer 10 and 11 spacecraft completed their missions within the solar system, they continued on, but their trajectories were not what NASA expected. Rather, they were slowing down faster than predicted, and no one knew why. Eventually, with the help of a multitude of other researchers across the globe, Slava Cherfev reported that the heat of the spacecraft itself was causing the deceleration. The effect is something like when you're driving a car and the photons from your headlights are pushing you back. This radiative momentum transfer was modeled to a high degree of accuracy. As it turns out, the deceleration wasn't just from heat directly radiating off the spacecraft and into space. It was also from heat radiating off the spacecraft, reflecting off this communication disk, bouncing back to the spacecraft, and then into space. How did the scientists figure this out? By applying the Flong shading algorithm. As the Pioneer anomaly demonstrates, even the smallest forces spread across time can make a very big difference. Fortunately, software doesn't weigh anything. Or does it? Barry Bain tells the most wonderful story about the incredible lightness of software. This is a story that I heard secondhand at TRW, but it may be an urban myth. It's about a weights engineer on a spacecraft. He accounts for all the weight on a spacecraft. The weights engineer came to a software engineer and said, according to budget, there is a $3 million accounted for the software, and I want to know how much it weighs. The software engineer replied, nothing. The weights engineer said he wanted that kind of a job. You get paid well to produce something that weighs nothing. A week later, the weights engineer came back with a deck of cards. Is there any software in here, he asked. The software engineer said, yes. The weights engineer said he would like to weigh the deck to determine the weight of the software. The software engineer said, you have it all wrong. We only use the holes. Software, it's in the holes. The trick, of course, is putting the holes in exactly the right place. If you want to be very pragmatic, while software itself might not weigh anything, the memory that holds that software does weigh something. Therefore, the more software you pack onto a spacecraft, the more it will indirectly weigh. Now, if you also want to be excruciatingly precise, the flipping of bits sheds thermal energy, and thus there will be a very subtle differences in radiative momentum transfer when an onboard computing is computing and when it is not. So, although software has no weight, you might have to design it to compensate for objects that do have weight and move. For example, imagine that your spacecraft is moving very, very fast, fast enough that you must account for Einstein's special theory of relativity. This is the situation with GPS satellites. Ignoring time dilation, they would be off by 38 microseconds each day. As such, the GPS system must compensate for these relativistic effects, else any mapping applications that use timing information from those satellites would slowly drift out of whack. Spacecraft exist in the real world and are subject to the very messy forces of the real world. It's therefore a very good idea that the typical programmer doesn't have to deal with problems of weight. This would vastly complicate the development of websites. From the inside of a software-intensive system across different domains, there are many different styles of implementation, each with its own subtle characteristics and idiosyncrasies. From the outside, however, especially to someone who isn't a developer, this software in every domain appears not just weightless, but also invisible. To the outside, it's all just holes. How then does a computing insider explain to someone on the outside just how beautiful and elegant and dramatic and messy and wonderful it is on the inside? This is a conundrum. I suppose one must begin by attending to the more fundamental question of why anyone from the outside should care. To attend to that second question, first I refactor Sagan's classic statement, observing that we live in a society exquisitely dependent on computing, in which hardly anyone knows anything much about computing. For our generation, and for generations that follow, we all use the artifacts of computing, but now must learn the skills of computational thinking, a concept first developed by Seymour Papert, and now further developed at Carnegie Mellon's Center for Computational Thinking. Back to the first question, I'd observe that one must start with some basic skills. It's hard to unpack the enigma of Bach, the chaotic beauty of Jackson Pollock, or even the raw energy of Skillerix without having some underlying appreciation for the respective medium. So it is with software-intensive systems. You at least need to grok the language of the medium, and only then can you begin the journey of understanding the nuances. What skills should we teach? Please understand that I'm out of my domain here. I'm not an educator, and I don't have any credentials to formally know what works and what doesn't. That being said, I am encouraged by the reality that there is an abundance of resources, from Code.org's Hour of Code, to the Code Academy, to even the Khan Academy. For those with more hands-on inclination, there's the Raspberry Pi and the Arduino, in all an embarrassment of riches. Yet, we must be realistic. Not every child needs to learn to code, but each one should learn some elements of computational thinking. And not everyone will care to become a programmer or software engineer. However, it's a start, the start of a journey of understanding how something that weighs nothing can change the world.